it up on the Twitter account as well, just in case those that needed the link can access it as well.
We're recording, so you can feel free to go in.
Okay, excellent. Well, I want to just make sure I thank everybody for joining us. Greatly appreciate it. Following us, we decided to do another webinar in regards of libraries because it's a very common topic, and we always are able to bring in some new ideas that maybe have been shared through the forums and whatever new implementations we do. We understand this is a very delicate process, so we hope that this is of benefit for all those. So my name is Ed Robledo. I'm part of the CAD Soft support team. I'll be doing the initial portion of the presentation. We're also joined by George Garcia, a resident expert over here in CAD Soft Computer. We're both located in the offices here in Fort Lauderdale. If you have any questions, I'll do my best, or George and I will do our best to monitor the chat as well as the Q&A section of it. So if you have any questions, feel free to post it. We'll try to address that question as soon as possible, or if we feel that at some point during the presentation we're going to be addressing it, we'll just continue. So, so you could always reach us at support@cadsoftusa.com. And if you have any questions after it, we are recording the session, and we'll make it available to everybody that decides. We'll send it to everybody that has registered for the webinar as well, okay? So I'm going to go ahead and begin with a few slides. Okay, so the agenda today is fairly, it looks short, but it is aggressive. So I'm just going to give you a slight EAGLE overview, an overview of the different portions of the library editor. The EAGLE library editor actually consists of multiple editors, and I will just give you a brief overview of that. And also, we're going to have a small chat or a one-slide overview of a third-party tool that we have gotten together with PCB Libraries, and we're actually selling this third-party tool at a very aggressive pricing structure. And this is an interface that allows the users to make EAGLE components in a very fast manner by just following the specifications on your spec sheet. So I'm just going to go through some slides, and George is going to go live with the entire presentation, okay? So if you're kind of new to EAGLE, this is a great webinar to be participating. So we're going to be breaking down exactly how the library works and how to go about it. So we really hope that you're able to participate. So just in case you're really new to EAGLE and you're seeing EAGLE for the very first time, I just wanted to add this slide. That way you understand exactly what EAGLE consists of. And what is EAGLE? EAGLE is basically a printed circuit board design program that consists of a schematic editor, a board layout editor, as well as an auto router. It's 3 modules. The schematic editor is a logical representation of your design, while the circuit board is actually a physical aspect. So you're actually working with the physical aspects of your circuit board. In EAGLE, we do have the feature that the schematic and the board actually work together. So modifications done to the schematic automatically update your board, okay? And the third and the final is the auto router. A lot of times when you go, when you go from the schematic to the board, the connections are defined, but they don't have a path. The job of the auto router is to do a really good, cost-effective job in which it takes those connections and converts them to an actual copper path, okay? Now, I was telling you that EAGLE Library Editor consists of 3 parts, and let me just give you an idea of what it is, okay? So our libraries, we have approximately I think it's over 300 libraries. Each library consists of anywhere between 25 to 35 components, okay? You could alter some of our existing libraries. You could create your own custom libraries, or you could actually get specifications from a manufacturer and use those specifications to build your own components. Now, component creation basically consists of 3 stages, okay? Now stage 1 can vary. Well, first of all, I'm going to start with the package. The package, when we talk about a package throughout this presentation, we're talking about the physical aspects of the component, either surface mount or through-hole or large ball grid array component is the physical aspect. So when you're in the package editor, you got to make sure that you're using the actual measurements and lead spacings of the component and the actual characteristics of each pad as well as its outline. The second portion of the editor, the second editor within the library editor is called the symbol. The symbol editor is actually the logical representation. What does this, when an engineer looks at the schematic and sees this component, will understand that, okay, that's a transistor, that's a diode, that's a resistor. It's a logical representation. When you put all this together in the EAGLE library editor is when you get to our third editor, which is called the device. And basically when the device is where we say, okay, we're going to use this package, we're going to use this symbol, we're going to put those together, and that's called our device, okay? Each one of the pads on the physical footprint is assigned to one of the pins on the schematic symbol, okay? Now, the package editor, basically you select which grid you're going to be using. Now, this grid is very important because this grid is the one that's going to allow you to do the appropriate spacing that is going to be needed between each one of your pads. You're going to define your component outline as well as the reference designator, the variable where the reference designator is going to appear, as well as where the value of the component is going to appear. One highlight I like to do here is that in the EAGLE board layout editor, you're going to see a button that says Design Link. It looks like this one quite a bit. It looks just like this. If you're using EAGLE 7.5, this is what the Design Link button does. And Design Link actually gives you full access to the entire catalog of components provided by NORC Element 14. Not only gives you access to it, it allows you to get specification sheets that they already have in their library. So you could type in the component that you're looking for, and it will find that component, and you'll be able to get the specification, pricing details as well as how much they have in stock, okay? Now, the package editor supports through-hole and surface mount components. Components are usually built on the top side of the board, and then once you're actually working on the board, you could flip it between the top and the bottom, okay? So this is what basically a rough rundown of what the package editor does, okay? The next portion is called the schematic editor. This is where you're going to actually be building a schematic symbol representation of the physical footprint. This is this portion. Now, what's really important, my PowerPoint is just like on a timer, George. It's just running on its own. I'm trying to hold it back. Okay. Now, it just keeps on running on me. Okay. I guess I was using it somewhere else and had it self-running. Okay. So, the schematic symbol, and George is going to highlight this as well, but it's really important that you work, when it comes to your pin placement, these pins that you're placing here, the pin placement, it's really important that you do it on a 0.1-inch grid. I can't stress that enough, okay? So when you're placing these pins down, it's actually you do this on a 0.1-inch grid. It's really important that you understand why, because when it comes to the schematic editor, the connecting point of the component are actually at the intersecting points of the grid. So it's really important that when you're placing the pins of your schematic symbol, you're working on a 0.1-inch grid, okay? Okay, so here you're actually going to place your pins down. You're going to give them a name. You're going to use the name command to name your pins accordingly. And you could use the wire command to create kind of an outline of what the representation of, the logical representation of this component does. So this is now the schematic symbol. And the third and the final step of creating a component in EAGLE is basically called a device. What we do here is that we just take the schematic symbol, we bring it in our device, we bring in the package, and what we do is that we tell it which pin is assigned to which one of the pads on the footprint, okay? So that's basically what a device is. So you say, this pin goes to this pad, this pin goes to this pad. Now, the nice thing is in EAGLE is that you could have multiple packages for the same schematic symbol, and that's what this portion here in the bottom you see is called variant. George is going to be going into this as well. So if you have the footprint for through hole or footprint For surface-mounted pad, you could bring them both here, assign each pin to each pad, and then you can make the decision on the layout if you want to use the surface mount or the through-hole version as well. Okay. Now, our third party, we got together with a company called PCB Libraries. They make a great library editors, one of the nicest ones we've been able to see out there. And the nice thing is that you're able to basically provide all of the specifications of that you have from your specification sheets from the manufacturer. You could enter that data and basically tell it to build a component for you. And then it will export that. It will export this in a format in which EAGLE can import it. It only takes a few clicks, and you could alter many components or only do the one custom component that you're creating. And George is actually going to be going through a demonstration of this as well, okay? If you have any questions, feel free to please contact us at support@CADsoft USA, or you could contact me as well, okay? So I'm going to go ahead and put George, that way he could go live with EAGLE. And thank you very much for your attention, and we'll be monitoring the chats. In case you have any questions, we'll take care of them immediately, okay? George, can you take it then? Or do I need to pass it to you? Okay,
no, I'm taking it.
Thank you, George. Appreciate that.
Okay, so you're stop sharing your screen. Okay, I'm getting. Is anybody having issue with audio besides Tyler? I saw here through the chat that the audio's cutting out every so often. Tyler, the only thing we can suggest is to call in. Sometimes computer audio is a little finicky. So if it's possible for you to call in, that usually works well. Okay. I'm going to go ahead and share my screen with you guys. Okay. Perfect. We are still recording. Bring up EAGLE. Okay. So a couple of things we want to cover before we actually get to the part creation is the resources you have for finding libraries and for creating your own parts. These days, you almost never have to create a part from scratch. You can usually reuse an existing part and modify it to suit whatever component you're trying to use. And that's usually a lot faster than having to calculate all the pads and draw everything out from scratch from the beginning. So what are your resources? Within EAGLE, your best resources are the ref packages libraries, which are right here. I have one of them open. Ref packages and ref packages on pad. Okay. Most of the standard packages you're going to find in here. So usually this is a useful basis for making your own parts. And you can search by looking for dual inlines, for different surface mount components, so on and so forth. Key point that I want to bring up to your attention. This library does not appear in the schematic editor. Neither does the other long pad variation or the SMD IPC library. Because they contain only packages, there's nothing they can bring into the schematic editor so they don't show up. So if you need to search for packages, the best place to do it within EAGLE is from the board editor, not from the schematic editor. Okay? So there's ref packages on pad, ref packages, the normal one. There's SMD IPC, which is useful for surface mount components. So this is another good one to check when you're looking for material to make your own parts. Okay, and the SMD, no, just those. So SMD IPC, ref packages, and ref packages long pad. Those are the three main libraries that you can use to get packages for your own parts. Again, if something doesn't perfectly match, but it's close, you can still adjust it and play with it. So these are the resources within EAGLE for source material. Now, online, there's a few places you can check. Obviously, here's Element 14. They have a large library section. Let me go ahead and get to it. Here we go. Okay. Here we go. CAD Libraries. Okay, here you'll find several libraries from all of our manufacturers. Some of our users have even compiled them all together into one file that you can download. So there's about 30,000 parts here, if memory serves. So definitely a good resource for finding parts as well. Another location you can search is our own website under Downloads, Libraries. Okay, we have several, I think there's a few hundred libraries here. Libraries here, and you can just search based on a word. So like previously, I was searching for tubes.
Nice.
We can hear you, Ed. Sorry about that, guys. Like if you search for tubes, you'll find several libraries here. Any component parts. Specific component parts can be a little difficult sometimes just because depending on whoever made the part, their descriptions are not as exhaustive as they should be. But this is usually pretty good. Okay, and finally, there's this one, which is Schematicpalcom. Now, this is to EAGLE what Google is to the Internet. Okay, you can actually search for any part here, and this site basically goes through all of GitHub searching for it. So we can put any part here. You know, something like, I don't know, we just do a pick 24 asterisk. We can use asterisk, any sort of wildcards. Okay, if the part is anywhere on GitHub in a version 6 or newer format, it will pop up. So go here, you can download the device and get all associated packages, so on and so forth. So this is one we recommend to users a lot, especially if the other methods didn't work from Element 14 or you couldn't find anything on our libraries, then this is another really valuable resource for finding parts. Okay, so those are your resources. Within EAGLE, you have ref packages LongPad, SMD-IPC. Online, you have Element 14, our website, and Schematicpalcom. Okay, so those are the main sources you can go to looking for parts. Now, despite the number of parts that all of these resources together can provide, there's no such thing as a comprehensive library. Not even the high-end packages have comprehensive libraries. They may have very large libraries, you know, 1 million or 2 million parts, but there are unfortunately more electronic components in the wild than that. So no tool can have an exhaustive comprehensive library. So sooner or later, and we highly encourage you to run into this as soon as possible, one of the first things you should learn with any CAD tool in EDA is learning how to make your own libraries. Okay? So that's what we're going to go through here. Before we do so, let me show you a couple of the new things in 7.5 as far as libraries go. Here's a section for the Element 14 libraries that you may download. I have it empty as of this moment. But here's a link to it directly from within EAGLE. And we also have libraries from Seed. Okay, and this is Seed Studio. These are components that, if I recall correctly, if you use these components, you can get a discount on manufacturing with them. It's kind of like a preferred parts list for Seed. So this is something, you know, if you intend to use that manufacturer, you may want to go into this library and see if you can use their parts to increase your cost savings. Before anybody asks, this is version 7.5. These icons are not the standard set. Version 7.5 allows you to modify icons and make your own set. And one of our users made a brighter colored set, which I enjoy personally. So I switched my icons over to that. So before anybody asks, this is a new icon set with modified colors by one of our users. And you'll see something similar in the other windows, not to alarm anyone. Okay? So let's go ahead and start. We're going to go File, New, Library. Okay? And this is how a brand new library opens up. It's completely empty. We have no symbols, no packages, no devices. The part we're going to be making today is the L293. I'll show you guys a data sheet. Okay, it's a quadruple half HBridge driver, usually used to run stepper motors or to create DC drivers as well. So it's a very versatile chip, very common. And we're going to be using it as a basis for our example today because we can cover a lot of ground just by making this one part. So it's going to be our focus today. So a couple of things I want to note. If we notice this part's available in a dual inline package, okay, which is PDIP, and it's available in this HSOP package, okay. So what we're going to do is, I'm pretty sure EAGLE already has this part, so let me see if I can find it, and if it has the DWP package. Let's say for the sake of argument in our application, that's the package we want to use, the L293 DWP package. Okay, so that's what we're gonna base this design around. So I'm gonna go over here. I'm gonna minimize this. So because I'm looking for a complete component, I can search in the schematic. We can go through the schematic. We can also do a search through here. We can do a search in tree. And see if we can find anything. Normally, I like to go to the schematic. I feel it goes a little bit faster. But let's see if we get anything over here. Okay. So a couple of things. We found this one in the seed library. It's not being used at the moment. Not the package we're looking for, though. Only the DIP package. So let's see if there's any other results over here. Let's go down. Got anything else? Hit next. There I go now. Popped up again. Not the one I'm looking for. Next. This is where? This is
down low, where it says driver, George.
Yeah, but still not the one I'm looking for. I was trying to see if I can find the DWP. And here's where I mentioned that searching from the control panel can sometimes be a little bit time-consuming. I usually find the schematic editor to be a bit faster. So I'm going to let this one finish out, but then from here I'm going to go back to the schematic editor. The advantage to searching in the control panel versus the schematic editor is that searching in the control panel searches everything. It searches for packages, for symbols, for devices. So there's no chance of missing anything here. In the case of searching through the schematic, you're only searching through devices, which is also why it's much faster. So again, we found the part, but not the DWP that I wanted. So let me see if I can find anything else. Another one. Well, looks like it may have it. Let me see over here. Symbols. Let this finish out right here. And that'll be it. I think you guys get the idea. So what I'm going to do is I'm going to select one of the previous ones. Now, for a part like this, some of the ones that we've run across would work, but we're going to finish through the example just so you guys can see, and if you go through the exercise yourself, you have a point of reference. So I'm going to go ahead and just see if I can stop this right here. Hopefully I didn't kill EAGLE itself. If there's any questions thus far, please feel free to ask them while we wait for this to finish. It looked through my own parts. That's good to know. Okay. So let's go back over here. And get the one from the SG Micro. Grab this one. Okay. Now this one I find for the most part suitable. Okay. So I could go ahead and copy that. I'm going to copy this one. So you can say right-click here, copy to library. Okay, now this is in my library. If I go to the table of contents view, I can see the 293DD. It's in an SO20 package, and here's its symbol. Yeah, we can check any of these out individually very easily. It is actually one of the nicer symbols I've seen, but we have a lot of grounds, so it's a little messy for my taste. This package, though nice, isn't a 28-pin package, so it's not what we're looking for our TI part. So not quite what we need. And the same thing for the device. The device is just using this, so not really what we want to have. Now, from the overview, we can remove any of this or all of it. Very simply, if we go here, we right-click, we have the option to remove. We can see what packages it's using, what symbols. Okay, so it's very easy to keep track. If, for example, you have a package and you want to delete it, but EAGLE doesn't let you because it's in use, you can figure out from the package which devices are using it, okay? And you can go and remove those or unlink, because in the librator, the device has control. Basically, because the device is the marriage of a package and a symbol, if you want to remove a symbol, you have to make sure it's not being used by any device, because the device won't risk its integrity by losing a symbol. So EAGLE simply won't allow you to remove it. So you always, if you need to delete something or get rid of it, you need to check the devices first. So in this case, let's say we just want to get rid of it because this isn't the part we wanted. We can go remove, see it's in use. But if I go to device, I remove this, remove the device. Now these two are unhinged from each other. So they're independent. I can remove them. I say yes. Remove. I say yes. I have a clean library again. I'm going to grab this one. Copy the library. Now the advantage, the reason I went with this one, is that this 16-pin pinout is pretty much what we need. If we go over here to, this is my additional notes. We go over here to the data sheet, we can see that everything pretty much matches what we needed to. So you can see that it was made pretty much following the package. So this one's okay. We have at least this package perfectly. But this one, we couldn't find really any trace of it. So this one we'll have to make ourselves. And that's going to be the exercise we're going to go through now. So we're going to go ahead and find a suitable alternative. Now to do so, you would have to know a little bit about the type of package. So if we go back to the data sheet, if we see here, you see this HSOP here? Okay. Usually, the last three letters are usually pretty standard. So, you know, dual inline package, you might see it as dual inline, DIL. The letters prior, anything before those last three, usually specifies a type of material or any special consideration or modification to the standard package. So in the case of these, the P is for plastic. It's a plastic dual inline package. In the case of the H, if memory serves, it's because of the requirement for a heatsink pad for this part. Okay? So what we need here is a 28-pin SOP package. Okay? 28-pin SOP package would be good enough for us to start. That way we don't have to make that package from scratch. So let's go over here to the libraries, and we're going to check. I'm not going to do the search down here again. But we're going to check in the ref packages library. Go here to ref packages, and it's organized alphabetically, so it's pretty easy to find the S's. See if we can find a SOP 28. We have SO 28. SOP 18, SOP 28. Okay, cool. Okay, SOP 28. Extra large. Let's go just with a standard one. Let's see if this is good enough for our purposes. I'm going to right-click, copy the library. So here's the package. A couple of things we want to check. Okay, you never want to take a package for granted. I'm going to set this to millimeters because the data sheet has everything described a little bit simpler in millimeters, so I want to do that. Millimeters here. I have that. Okay. So, in case of this one, let me go ahead and bring this down. We go to the data sheet, and you guys can verify this later. Okay, here we go. The separation between the pins is 1.27 millimeters. So visually, we can actually inspect that is the case, 1.27, because all of the pins are always lining up in the center. So we know that pin separation is okay. Now that part is fine. Let's check out the width here for these. The width of these pins can be between 0.5 millimeter and 0.35. Look over here. So here we have 2.2 is the length, 0.6. So it's a little too fat. Right? The data sheet gave us, is it either 0.5 or 0.35? So we can actually go ahead and change the sizes on these. We can go change SMD, and we can specify. So we can say 0.5 by 2.2, hit OK, and now all I do is click away. And you'll see that they will all thin out. I can do it as a group as well. Okay, perfect. We have that covered. Other thing we want to check is the size. Okay, the size should be about 10.65 millimeters, right here, between 10.65 and 10.16. And we really want to be able to do as much of a visual check as we can, because that here, the more things we can verify visually, the less time it takes to make adjustments. So from here, I have one. Let's see if it's 10.65. We divide it by 2 from the center, so that would be, we would need like 5 millimeters and a quarter roughly, right? So because we have this in 0.5 millimeter increments, so here's 1 millimeter, 2 millimeters, 3 millimeters, 4 millimeters, 5 millimeters, and like 5.5 here, right? So look, yep, 5.5 right there. So we can see here that this is a bit long, just a tad long. So
George, could you consider zooming in a little bit because it's so far out, it's hard for us to see.
So it's a tad long here for this part. So what we can do is we can either move these, we can make them a little bit smaller. We can also check the sizes on the side just to make sure that may be an easier check, because I get a feeling I may have accidentally grabbed the wrong part. It should be about 8 millimeters here, 7.6. So I get a gut feeling that I got the wrong one. Happens to everybody. 7.6 would be like 3.8 roughly. So yeah, this is a big part. It's too big. Got the wrong one. Whoops. That happened. So I grabbed the wrong one. Let me go back over here to the control panel. Instead of the stop, let me get the SO28. I think that's maybe what I used in the last demo. My body.
Just to let you know, guys, that also for those that are attending, if you have a library open and you have your EAGLE control panel side by side, you're able to click, drag, and drop a package or a device into your library, just to let you know. You could drag and drop as well.
Thanks, Ed. Thanks for the clarification. That is possible. That's another method to copy into your library. And this one is right now. This one's okay. This one, let me check the grid spacing. I'm going to put it back to 1.127. Okay, they're all centered. Sizing is probably off, so I can change that. Change SMD. I can make sure to use the same one I used before. I can group these. See if maybe control right click changes them. There we go. This one is correct. This one I just verified right now. Okay, again, control right click, and now we have them skinnier. Okay. Separation is what it should be on this one. I just verified that. So 0.5. If we look right here, we have about 3.5 at this point, so a little bit more. That's correct for the data sheet that we have here. Point here is 5.5, which is also okay. So this one very closely matches what we have on our data sheet for the requirement of this part, just by checking these sizes. Okay. So this is very good. I checked that, the separation, I checked it as well, so we're good. So we have verified that this package, for the most part, is suitable. What it's missing is the internal thermal pads. Okay? And that's what we're going to do now. I'm going to go ahead and handle the thermal pads. So as you can see, we have name and value. You always want to make sure to add those into your designs. Now, where can we find the thermal pad information for this part? Okay, if we go to the main data sheet, it actually has it as a note with a thermal pad. And the note says, package is designed to be soldered to a thermal pad on the board. Refer to this technical brief, blah, 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 blah. So if you go and find that technical brief on page number 9, okay? Here is the instructions for the thermal pad we wish to make. And I'm going to zoom this in just a little bit. Okay, and I've highlighted what each of the vias, what their drill value is going to be. It's going to be 13 mils. And this is the pad we need to create, okay? Now in EAGLE, the general recommendation is that you center your part. Okay, that makes it a lot easier for placement because you know the snap point's always here. And for calculating different points is also much easier. So in this case, what we're going to do is we have to make a thermal polygon following the directions here. Okay, it's a 6.5 by 17.91 thermal polygon. So we're going to do that in EAGLE using the polygon command. I've already calculated the points of this polygon, so we don't have to worry about handling that. We're going to put this on the top layer. Okay, we're going to put a, this is a, this is, I think a 50 mil width. Okay, should be okay. I may go with something smaller. I may actually go with a 5 mil width. Nice and fine. Okay, by hitting enter, I make that effect. So for the points, basically all the polygons have to start and end on the same point. So I'm going to enter those on the command line, okay, in millimeters. So assuming everything goes well, I should have 8.955, 2.25, and these are coming from calculations I did on the recommended thermal pad. I have that. Now, basically by changing the signs, I can get all four corners. I have 5, negative 3.25. Oops. Okay, now negative 8.955, negative 3.25. 8.955, positive 3.25, and then we're back where we started. So I say 8.955, 3.25, and as soon as I hit enter, we should see a polygon, and everything should be okay. Perfect. That should be okay. All right, perfect. We have that going for us. We're noticing that here maybe the length of this was not ideal. I could probably lengthen it out a little bit more if need be. Make sure that I made that right. Okay. So that's our thermal pad. So you can see there's a lot of length here. There could be some clearance issues, but normally it's not the case in the DRC with this part. I am going to verify the length because something seems off to me here visually. Okay, this length maximum should be 18.03. Give us 9. Yeah, that's right. Correct. Yep, that is right. And now we're going to put in the thermal vias. Now, there's a lot of ways we could do this. Again, I did the calculation, but I want to go ahead and leverage a tool that we can use to speed up placing these. So in total, I have 33 of these thermal vias that I need to place, 33 of them. So what I'm going to do is I'm going to click the via command. I'm going to set their size. You can just type in any size you want, and EAGLE will automatically convert it. So I'll put 0.33 millimeters, which is the equivalent of 13 mils. I'm going to hit enter. I'm going to make these circular, because I like the circles. And what I'm going to do is I'm going to just place 33 of them. So 1, 2, 3, 4, 5, 6, 12, 13, 14, 15. I got 33. Hit info on that last one. Yes, $33. And what I'm going to do is I'm going to use one of the tools that comes with EAGLE. That is ULP's component array. Very useful ULP that we want to become very familiar with. Like this one. Okay, and we can make a rectangular or a circular array. So the prefix here is $. I'm going to start with number 1. Okay, so it's going to basically arrange pad number 1 up to pad number 33. It's going to be in increasing order. The start point, I'm gonna put those in a second. It's going to be in millimeters. All units here are going to be in millimeters. We have 3 rows, and we have 11 columns. The start point is going to be the location of the first one near the bottom left. Okay, so for that one, I have negative 7.4625, and the y is negative 1.625. Okay, now the separation, again, I'll take in from doing some simple math, which I can show you guys. Okay, if we look here, there's 11 pads, right? So there's 12 spaces between them. So you take that length, 17.91, divided by 12, and that gives you 1.4925. Okay, that's the spacing. Same thing with the rows. You have 3 rows, there's 4 spaces between them. Take 6.5 divided by 4, and it gives you 1.625. So returning to EAGLE, our little UOP, those are going to be our separations. So in the X dimension, I have 1.4925. In the Y dimension, I have 1.625. Okay, this is ready, and I'm going to hit OK. And there we go, perfectly placed. Okay, imagine having to have entered every single point for this. Okay, it would have been a mess. Now, one thing here that's important that can get you in trouble. I'm going to say all, okay. If you notice, each of these pads has a stop mask opening, which basically makes sure it's exposed. But the polygon that I made, okay, this polygon is not exposed, and that will create some serious issues in manufacturing. So when you do this, you have to make sure that you draw that polygon again, but on the T-stop layer. Now, because I entered the points previously, if I press up, I have all those points. So I can cycle through any commands that I type in the command line just by pressing up and down on the keyboard. And now I select the T-stop layer. And I just hit enter. And now we have guaranteed that this entire thing will also be exposed, which is what you want for a thermal pad. Okay, so this essentially is the completion of the package. Any questions thus far, please feel free to send them into the Q&A or through the chat window. Okay, Now we're going to go on to the symbol. Okay, so we have this one, and I don't feel it's descriptive enough. I mean, in the most basic sense, you can do this. You can just make a rectangle, name the pins, and it's technically correct. But visually, it doesn't convey a lot of information. So we're going to make our symbols ourselves, and I'm going to make it following my little notes over here. I'm basically going to try to imitate this setup here. Okay, we'll have to change the names a little bit, but it should be okay. So let's go ahead and start making those. I'm going to go to symbol. I'm going to say call this HBridge because that's essentially what we're making. Symbol for an HBridge. I'm going to use the wire command to draw my little triangle. Now, as I was mentioning before, a very key point here is to use a 0.1 inch grid. Okay. The reason for this is that all of the components in EAGLE's libraries are made to this grid. If you deviate from it, you're going to have a heck of a time getting things to connect. Okay. Now, artistically, those features can move around anywhere. The real key point is that the pins, the electrical connection points, need to stay on the 0.1 inch grid. And we're going to see that in a second. So I'm going to use the wire command. I'm going to go ahead and say draw that. I can change mine to this, that. Okay. It's my little triangle there. Go ahead and make a copy of it. Copy. If I hold Control and right-click, I automatically apply the action. This is okay. I'm going to go ahead and make sure. Usually for alternate grid, I'll use quarter. I don't have to need a tenth of a. That'll usually be enough for me. So I'm going to use the wire command again. This time, I'm going to set the width of it to be a little bit smaller. And the reason for this is that the pins have this type of thickness, have a 6 mil thickness. Yes, have a 6 mil thickness. So if we notice, I can't really end on a nice point here. And this is where our alternate grid is going to come into play. And there we go. Same thing here. If I hold Alt, I can invoke that quarter grid. Perfect. Now I'm going to draw a little circle here. And if I set the width of the circle to be 0, it'll fill in. So that's obviously too big. But if I shrink it, I can get something like that, which is far more reasonable. Okay, so we have that. Go ahead and start putting in our pins. Pin number 1, pin number 2, pin number 3. And I'm going to use 0.06 that I have here. Take that to the center, just so that visually it makes sense. Okay, so this is starting to look pretty good. Obviously, this conglomeration of text here is not cool, but that's pretty easily solved. Another point here, you'll notice on the ends of the pins, these green circles specify the connection points. Okay, all of your connections have to be made at the center of a green circle. So if you're off from the center, even by a hair, the connection won't be valid. That's why it's so vital to stick to that 0.1 inch grid. Okay, and as you notice, statistically, I could draw anything I want, these triangles, that's okay. The pins have to be on a 0.1 inch grid. No ifs, ands, or buts about it. So what we'll do here is we're going to go ahead and start giving these names. We're going to see the options for the I/O direction. We're going to see what these pins here mean. Okay. So let's go ahead and go over here using the info command. Okay. We have the pin $2. I'm going to say this is A in. I'm going to call it that. This is B in. can also use the name command and just make it easy. This will be the enable. Okay, this is the output, A out, A out. Now, why have I chosen to go with this type of naming convention? The reason behind it is that basically I'm going to reuse this symbol twice to make the two HBridges that are in the component. Okay, and I could have gone about this a whole slew of other different ways, but this is the one I chose to for this application. Okay, basically one HBridge can drive one motor, so I like splitting them up that way. Now this is kind of ugly. We don't want to see all this. We can go ahead and turn that off. We go to Info, and we see the pin has this property called Visible. Okay. When it's both, it'll show both the pin name and the pad name. Right now we don't have it in a device, so it doesn't have a pad name. For our purposes, I would rather just see the pad. I think that's going to be the easiest way. Now I/O defines this pin as an input and output. We have other options. We can define it strictly as an input, strictly as an output, open collector, power pin, a passive, which basically doesn't receive any ERC checks, high impedance, or as a apply pin. Okay, for our purposes here, we can leave it as an I/O. In general, if you don't want to fuss with it, having it set to I/O or passive is the easiest way to deal with it. But if you can get some error checking if you assign a direction. So I'm going to assign this to be an in. Okay, the swap level basically dictates whether this pin can be switched for this pin or can be switched for any other pins of the same swap level. A swap level of 0 means the pin is completely unique and is not swappable with anything else. Okay? Here, this pin is the only one that affects this entry over here. So I'm going to leave all of these to 0. When in doubt, just leave everything to 0. So I'm going to go ahead and hit apply. Say OK. And now we have this in. This will also be an in. Set the visibility to be pad. We say OK. Here, in, and then this can be here, whoops, no. The length dictates how long this little wire attached to the connection point is. These will be outputs, and their visible will be pad as well. And we'll do the same thing here. There we are. So this symbol is pretty much complete. I'm just going to add in the name and value, and there's a lot of easy ways to do it. We can use a UOP called set name and value. I'm going to put these here, like that. Okay, so this symbol is pretty much done. Again, if there's any questions along the way, please feel free to drop them in, okay? So, only other thing we have to make here are power pins. Okay, because this component, if we look here at the data sheet, okay, if we look over here, we have, where is it? Okay, we have 2 VCC, we have 2 power supplies, and we have obviously ground. So the best way to handle that usually is to put those as a separate symbol. And we'll see the description of those here. That little document here that described it. Okay. So let's go ahead and make that symbol, and that'll be very easy. So go ahead and make another symbol. I'll call it power pins, P pins. Yes. This is going to have just 3 pins on it. 1, 2, 3, easy. and these are going to be power pins. You can always extend this a little bit, and I'll probably need to. Go ahead and start changing the properties here. So the name for this one, this will be VCC1. Will be VCC2. Go ahead and fix the power setting as well. Want both visible. The ground. Power. Fix this one. Now, I'm not super happy with this because it's very easy for me to forget which one's which one is the power supply for the logic, and which one is the power supply for the motors. So let's check over here real quick at our data sheet. Let's figure out which one is the one, which one is which. So VCC2 is for the motors. V2 is for the motors. So what I'll do is over here, I'm just going to change the name. I'll do the same here, VCC1 logic. Always make your schematics as easy as possible to read. So there we go. Perfect. Now, what's special about a power pin? Basically, power pins, 1, expect to only be connected to a supply pin, and 2, all instances of power pins are automatically connected. So if I had other circuits that had a VCC2 mode power pin, they would automatically be connected even if I didn't put a supply symbol. Okay, so that can be leveraged for connecting your components and really making it easy to follow your design. We have that. I think we're pretty much ready to make our variation of the L293. Let me just put in the name and value here as well. You can assign UOPs to shortcuts if it makes it easier for you. Go to the device. My L293D. Yes. So I'm going to go over here. I'm going to take this HBridge. I'm going to put in 2 of them. You notice that they get $1, $2. This is only apparent within the device setter. When you go into the board, you won't see that. Okay? You'll see, and we can change it a little bit, which is what I will do. Let me hit escape. Power pins, bring that in. So here, I'm going to go ahead and rename these. I'm going to name this A, this B, name this P pins, power. Okay? So what's going to happen is when power's going to be too long. Let me just name it P. When I bring these gates into the design, you're going to see IC1A, IC1B, IC1P. Okay, and then if I continue to put more, then it's going to continue to cycle. Okay. So, and that's dictated by the add level here. Next just means they go in order. Usually for power pins, we use a different option, and we use request. What this means is that by default, this power pin won't show up, which helps clean up, keep the logic of the schematic nice and organized without any extra clutter. It can later be invoked in the design. So I'm going to leave this one as request. Again, we have a swap level, which means if there's any equivalent. Now here, we can do a swap between A and B, and functionally everything will stay okay. So we're going to go ahead and do that. We're going to set the swap level of these to be 1. I have a swap level of 1. this means in our design, we can do a gate swap. Sometimes for layout reasons, it's easier to route on one side of the chip versus another, and that allows you to swap out the gates. Okay? So we're good there. Now we have 3 packages that we can use. We have the SOP 28, the one we made, and this one. Okay? So let's bring in, we can bring in all of these. If we had more pins than some of these had pads, they would be grayed out. So if you ever see that the package you want to use is grayed out, it means that the setup here of your symbol has more pins total than pads in your package. Okay, in this case we're okay. So I'm going to bring in the dual inline 16 because I do want to use that. Okay, and then I'm going to bring in this SO28W. Now just for the sake of argument, I'm going to go ahead and rename that. So I'm going to go here to the library view. When I go here SO28, I right click on it, I have rename. I'm just going to call it HSOP28. And I'll drop the W. Say OK. Now we can go back to the device. Go new, HSOP28. Now if I say OK, watch what's going to happen. It's going to tell me package variant already defined. This tends to confuse a lot of users. Okay. You notice here the first package has a null variant. Basically, it's an empty single quotes. Every subsequent package needs to have something to distinguish it. So in this case, I'll just use DWP, okay, to distinguish it from everything else. And say OK. There we are. Now it allows me to add the package. So whenever you're going to use multiple packages, always remember, the first one you don't have to define a variant name for. All the other ones you do. So very important. So for prefix, I'm going to put IC. If you don't specify a prefix, it's going to become $, which is not very nice. Value here. If it's set to off, then the default value is going to be the part name, the device name, and it won't be user adjustable by default. If we set it to on, then the value is going to be empty, and we can adjust it by default. So for ICs, normally you'll pick off. For passive components, you'll pick on. Very simple. Now we're going to go to connect. As we can see here, for this variant, here's all our pins. Here's all the pads that we can connect. Okay. So if we go back to the data sheet now, we can figure out how to connect what to what. So the A, we'll say the A gate is basically this top one here. Okay, so we're going to be connected to these pins. Okay, so AN is going to go to 2. The enable is going to go to pin 1. It's going to go to pin 7. Then the out for A is going to go to pin 3. And the out for that one is going to go to pin 6. Now we repeat that with the other gate. Okay, and again, just following the data sheet here. That one is going to be pin 10. 7 on that one. Enable is going to be pin 9. Pin 14. Now for ground, interesting. For ground, we have a lot of pins that have ground, including all of these inner pads. Go back to the data sheet, check it. And it's easier if we do VCC1 and VCC2 first. So VCC1 goes to pin 16, and VCC2 goes to pin 8. 4, 5, 12, 13, and everything else should go to ground. Actually, I think I've misconnected these. Whoops. Yes, I did. Did misconnect these. My mistake on that. Now, we're running a little bit out of time, so what I'm going to do is I'm going to, for the purposes of the example, you guys get the idea. I'm going to leave those, even though they're wrong. And then for the ground, I'm going to hook up all of the remaining connections. And this is very easy. I can do connect on that one. And as long as ground is highlighted, I can hit append and just tack on everything else. All the remaining pins, I can just tack them on. This is how we assign multiple pads to a single pin. Now, you notice we can expand and see all the pins that are assigned there. We can disconnect all of the pins. And we have this little icon here. Now, this little icon is very important. This little icon in this state basically says that for the netlist to be satisfied, all of these pins need to be connected to that ground signal. Okay? If I click it, we're going to see that that little wire in between leaves. And in this configuration, it says as long as one of these is connected, then the netlist is satisfied. So you would use this option in the case, for example, where all of the pins are internally connected, and you don't want to require every single one to be connected. This would be a good option here. The other one is pretty much a strict necessity if there are separations within the IC, which can happen like in the case of digital and analog grounds. So we can say OK, and now this one is satisfied. We can do the same thing here. We can make lots of connections. I'll just go in order. I'll tack these onto ground like the issue says. This is OK. And voila, this is a complete part. Normally, you can also add in a description, quadruple, half, HBridge driver. This accepts full HTML, so you can link images here. You can put links to data sheets. So this accepts a good subset of HTML. So it really helps you document the library. So I'll say OK on that. And this is pretty much it for the part. Okay, this is how you make a library. So the only other thing we want to do is we're going to go ahead and save this. I'm going to go ahead and save it in my LBR folder. I'll get rid of it later. Okay, it's saved. Now, if we want to use it in a design, very simple. Go File, New Schematic, Library, Use. Every library needs to be put into use. Okay, so I'm going to go to my C drive, select 7.5, select my LBR, find that Creating Components library. It'll be in the C's. All right, double click it. Second. Okay, and then now here, go to the add, and it will show up. And I can bring in my parts. Here's my two package variants. And you'll see, once I put these in, power pins don't come in. To bring them in, I can do it by using the invoke command, which is this one. So I click on any of these, and I can bring in the power pins. Okay, really simple. So that's creating your own parts, okay? straightforward, nothing too crazy. I want to show you now a couple of other resources you do have at your disposal within library creation. Okay. Now, let's say you can't find a suitable package and you do have to make it from scratch. There are several tools that come with EAGLE that can simplify this. So we have, go to UOPs, and the one we're really interested in is Make Symbol Device Package BSDL. This is EAGLE's part creation wizard UOP, okay? Very useful, very powerful, and in a lot of circumstances will cover most of the cases that you're going to be using it with, okay? So, for example, it can make BGA packages, it can make standard packages, you can select different configurations of duals. Basically, all you have to do is specify the parameters for it, okay? Now, another really cool feature of this UOP is that it can take in BSDL files. For really high pin count components, usually a BSDL file will be available. Let me show you kind of what it does with it. Go browse. I have one in my webinars folder from a previous session that we did. So, say open. And here's the full text of that BSDL file, very long. And what you'll see is that it creates all the pins. Okay, it has a symbol specified, has a package specified. We can adjust, according to the data sheet, we can adjust the parameters. Okay, I'm just going to use this one by default. It may not work. I'm going to accept it. And you see it has symbol name, device name, package, everything is here. I'm going to say OK. And what you'll see is that it makes the symbol for you perfectly. All of the pins, everything is named. It makes a package. Now, I didn't adjust any of the sizes, so it's going to be wrong. But you can see that it created it. And it automatically did all the connections for you. Okay, so next time you're using a 400-pin FPGA part, ask the manufacturer for a BSDL. If you can find one, you've got all of this done for you. Okay, so very awesome UOP. There's a lot to it in the documentation tree. You go to Control Panel, you go to Documentation tree. You'll find the full manual for it. Okay, UOP is right here. This one. There's a manual in English, manual in German. Okay, and it's actually a pretty long manual. This UOP can do a lot of stuff. So it goes through an example using the BGA, making your own symbols. It's a very, very strong UOP. Highly recommend checking it out. It works like a wizard, you know. So you usually don't have to go through the trouble of calculating stuff yourself and things like that. So those are all the resources I wanted to show in EAGLE. I would now want to take a moment to show you PCB Library Expert, which is our new third-party partner. Okay, this is a beast of a tool. This is a very, very insane tool. This is the natural the next step over that Make Symbol BSDL UOP I showed you guys. This is the next level up, and it's very easy to use. Okay, in its simplest form, it has wizards for surface mount components and for through-hole components. Okay, so we have wizards, very simple. For all sorts of standard packages, we have, headers, dual inlines, all sorts of stuff is here. Okay, same thing for surface mount. Dips, PLCCs, fans, you name it, there's something here for it, okay? Dot packages, it's all here. Normal transistor outlines, it's all. So, how does this work? Okay, in its simplest case. Let's go ahead and let's make a dot package, okay? Basically the same one we had before. So we're going to click here. Now, when you use the wizard, it doesn't let you get too fancy with thermal pads and stuff. This is just for making the base package. Okay? Again, for the purposes of time, I will mention how to get the thermal pads in, but most of the use cases will involve using it here. Okay? So real simple, just off the data sheet. Okay? We find the pitch in millimeters because that's the units we're working in. It's 1.27 millimeters. This package has 28 pins. Now A, you just look at the picture. According to the data sheet, it's 2.65 millimeters maximum. A1 is, the minimum A1 is 0. What is it? Here we go. 0.25 millimeters. Okay, the B is the thickness of these. Now the thickness of these, if you notice we have a minimum and a maximum, it's 0.5 millimeters, 0.5 millimeters according to the data sheet. Okay, the D, that length, according to the data sheet, can be between 17.7, 18.1. Okay, the E, be 9.97, 10.63. E1 will be 7.4, 7.6, and then the L, according to the data sheet, can be between 0.4, and 1.27. Okay? We filled out the table, say OK, and there's a footprint. Okay? So for any footprint supported by the wizards, it's as easy as that to make your part. Okay? Now, a lot of the parameters, keep out areas, silkscreen thicknesses, all of that is actually defined under preferences. Okay? So in the preferences, you can see different rules for different items, stuff you can adjust, you can make new ones. You have the default, IPC defaults right here. Okay, you can create your own. Now, what's really, really impressive about this tool is that after you build up a library within it, let's say you change manufacturers and they want the silkscreen a little bit thicker or some other modification. If you set that up as a rule, you can actually rebuild the entire library to conform to that set of rules. So in a given moment, let's say you have a library of 20 parts that you use, and you need to adjust silkscreen thicknesses, keep out separation, that type of stuff. You can do it all in a flash by changing the preferences setup and then just building the library. Okay, in this case, it shifts with the default library here. Okay, all of these parts conform to the default preferences. If I change them, in a second, I can build the whole thing again to conform to a new set of parameters. So it's very, very powerful, very flexible. For our purposes here, we can just build the part. Let's say we're happy with it. I want to put a pin 1 marker. Adjustments. Okay. So what we can do here is go ahead and just build the part. You'll see we have the option to export as a 3D step file because we entered the height, or we can export it to EAGLE. And this is the name it's going to go out to. Outline width, reflect the 3D height. This is useful for certain UOPs. I'm just going to output it to the desktop. Okay, say OK. All right, I'm going to say create very fast, and it's done. Now, what it's exported here is not a library file, just so you guys know. Okay, I'm going to close this. So if we go to the desktop, what we actually have is a .scr file, okay, which is this one right here. To make it into a library part, we go to our library. I click on the script desktop, on my script, layer 1 tab, okay. There we are. We zoom in, see everything here. And that's basically the way the part was made. Info, here's a T-stop. Here's our pads. Okay, so everything is here. Now it's not perfect. It does. We got to give it a little bit of feedback because it seems to create twice the name and value. Create it twice, but that could be my user error. But as you can see, there's a lot of potential in that tool. Okay, if you needed to make something outright, something really like unique, then you would go into FP Designer. And this thing covers all the bases. I mean, you can add so much stuff here. It's really, really silly. A lot of control. You can start adding different pad stacks and different, I mean, it starts getting pretty crazy. And I personally haven't worked through the whole process myself for making a footprint using this tool from scratch. But again, it follows the same wizard type style, as you can see here. So this is the Library Expert Pro demo, as well as the component, creating your own components webinar. If you guys have any questions, please feel free to share them now. Okay? I'm going to go ahead and stop sharing my screen. We have 2 questions from Jean. Okay, so what swap level would you use for a 2-input NAND? Okay, for the 2-input NAND, for the pins themselves on the inputs, you could set the swap level to be the same. The key here isn't the number itself. Basically, as long as 2 pins have the same swap level, then they're considered to be interchangeable. So in the case of the 2-input NANDs, each of the input pins would have a swap level greater than 0. It could be 1, it could be 2, it could be whatever. Okay? Please email the lib we just made to the participants so we can examine in detail. Okay, I will do that. I will probably post it up for download or something. I know what I'll do. I'll put it on the webinar page. That way you guys have access to it, and it'll be a nicer one because this one I made the mistake when I was connecting the pins, so I'll give you the correct one. Okay? Any other questions? Okay. If there's nothing else, I want to thank you guys for taking the time to be in this webinar. I did record the whole thing, so we will be posting it shortly, okay? And I will also put it on the webinar page on Element 14, okay? So thank you very much for your time, guys, and have a great day.